Okay, welcome back. So after a 1 week break, we're back to our lectures, and we start with a new chapter today. It is called Random Vectors. So it is the third chapter. Random vectors. And we're going to start by discussing product spaces. So far in this course, we looked at random variables taking values in a measurable space, right? And most of the time, this measurable space is nothing but the real line or extended real line. So we looked at numerical random variables. So the term random vector is used for nothing but a collection of finite collection of random variables. Okay, and this vocabulary is mostly used in the setting of random variables or a bunch of random variables that are just numerical. So if you have 1, 2, 3 random variables that are numerical, you just call this collection a random vector. Okay. But as we will see in this course, in this chapter, random vectors are nothing but random variables. All you do is to look at a measurable space that is created as a product of a bunch of measurable spaces. So this is the idea of product spaces, and this idea is not very new to you because you know, for instance, R2, R3, Rn, right? Just the n-dimensional Euclidean space. What is that? It is just the Cartesian product of n real lines, right? But the new question here is the sigma algebra. So let's say you have a Cartesian product of bunch of spaces. Let's say R times R, which gives you R2, okay? So what is the sigma algebra on R2? Okay, that's going to be the question. But once you decide on your sigma algebra on the product space, on the Cartesian product, the rest is, it comes for free from the earlier theory, from the first part of the course. Then you can talk about measurability of functions. Then you can talk about distributions of random variables, etc., etc. Now random vectors. Okay, so this term random vector is therefore used for nothing but finite collection of random variables. For instance, we can have some motivating example, okay? Let's say coin tossing, okay? Let's say you toss a coin, tossing a coin 10 times, where your probability space is the Cartesian product of this set 0, 1 by itself 10 times. So which is the sequence of finite sequences of length 10, right? Where each term here is either 0 or 1 for each I between 1 and 10. And of course, this is a finite set. Well, Cartesian product of finite sets is, again, a finite set. Therefore, you can just use the power set as the sigma algebra, right? You can equip this with the power set, the discrete sigma algebra. And let's say this is the discrete sigma algebra. Okay, so then you can talk about a bunch of things, right? So if this is a coin tossing example, you can talk about the number of heads up to a certain point, right? Maybe number of heads in the first toss, which is either 0 or 1, right? Number of heads in the first 3 tosses, which can be 0, 1, 2, or 3, right? And number of heads overall, okay? Which is a number between 0 and 10. You can talk about a bunch of random variables, right? So let's say Sk is the number of heads. Well, for us, the heads is 1 and tails is 0, right? If you remember, we consider heads as success and 0 as failure or tail. Number of heads in the first k tosses. Well, we have in total just 10 of them, so this k is between 1 and 10, right? And if you want to write it down precisely, well, this is a finite sequence, right? So what is the value of it? How do you define it precisely? What is sk of omega 1 to omega 10? How would you count the number of heads in the first k tosses? If you're given the outcome, omega equals omega 1 to omega 10, just bunch of zeros and ones, right? So how can you count? From 1 to k, right? The first k tosses. So this is omega 1 to omega k for every omega. This is what we mean by defining a random variable, right? You can informally, or you can define it in words like this, but this isn't a mathematical definition, so then you can just write it down precisely as follows, as here. Well, of course, this sk is a numerical random variable, so we know everything about it, right? We know what we mean by its measurability, et cetera, et cetera. What do we mean by its measurability? Who would like to recall? What is the measurability of sk? So how can I check if sk is measurable? What kind of a random variable is this? How many values can it take? sk, how many possible values? Not 11, right? K plus 1, yeah? So, well, it's just discrete, right? So how can you check the measurability of this? Measurability of sk, how can you check the measurability of sk?
You take the events, sk is equal to I.
Yeah.
And those events should be
in the sigma algebra, right? Well, here, this question is trivial because we took the largest possible sigma algebra. So it is always yes. It is always measurable. So whatever you define on the space, it's going to be measurable. Okay? But in general, this is what we do, right? So measurability of sk means, or it is equivalent to, checking that sk equals, let's say I is in F for all I, well, all possible values, right? It starts from 0, it goes up to k. And in our example, this is always the case. It is always a measurable function because we took the discrete sigma algebra, the power set. Okay? So, in other words, the question of dealing with just one numerical random variable is not very interesting for now. Okay? So after the first half. But let us define a collection, a finite collection of them. Let's say S1, S3, and S10. Now what is x of omega? Well, it is S1 of omega, S3 of omega, and S10 of omega, which is a vector in R3. You can make it a smaller space, of course, because S1 can take only the values 0 and 1, S3 can take the values 0, 1, 2, 3, and S10 can take all the values between 0 and 10, all the integer values. So you can also write down a more specific Cartesian product of 3 spaces, but we can safely say it is just a point in R3, the value of x. Okay. So the questions of interest for us are as follows. For instance, what is the sigma algebra on R3? What is the, let's say, canonical, and by canonical I mean Borel, okay? Is there a Borel sigma algebra? Borel in what sense, right? Borel sigma algebra on R3 so that we can treat x as a function from omega to R3 and talk about its measurability. What is the canonical sigma algebra on this product space, on R3? Right? R cross R cross R. And okay, once we discuss measurability, what is next? So once you decide on the measurability of a random variable, of a function, what is the next question? What do you look at? Whenever you have a random variable in the probabilistic setting, what do you look at? You want to compute something, right? What can you compute? What do you want to compute? Expectation, or in general, it's distribution, right? So given a probability measure P on omega F, what is the distribution of X under P? Then, of course, you can ask about its expectation. Well, now it's going to be a vector, right? Expectation is going to be vector, right? And we're going to define it as the expectation of this, and expectation of this. But we're not there yet. Well, the distribution is an interesting question. And as a follow-up question, so how about the infinite case? Infinite case. Then you can talk about infinitely many things, right? First of all, your omega is infinite. Your omega is infinite. Yeah, it's an uncountable set, 0, 1 to n. Okay, so we defined a sigma algebra here at the very beginning of the course as the sigma algebra defined by those events. So A1 is the event that you get heads in the first toss. A2 is the event that you get heads in the second toss, etc., etc. We're going to look at that question from a different point of view and redefine the sigma algebra as a power sigma algebra. Okay? So your domain of the function, the domain of your function can be a Cartesian product, and the value space, the image space of your function can also be a product space. Okay? You can have R3, which is a product space, and you can have omega, which is itself a product space. And here it is an infinite product space, which makes it even more complicated. And you can talk about infinitely many random variables here. Okay? For the infinite case, we're going to do it later. Okay? So later, not in this chapter, in chapter 5, I guess. For now, let's just look at two spaces. Okay? Two spaces. So product of two measurable spaces. Any questions so far? Any questions about our motivation? Why we would like to deal with products? Any questions? Okay. So now I would like to isolate some abstract structure from this example. And just for simplicity, I'd like to deal with just two spaces. Okay? So let's say we have two measurable spaces. And in your mind, you can always take them as the real line with its Borel sigma algebra. That's going to be the example that we're going to discuss. Okay. So the product of E and G is defined as a Cartesian product. And this is done in the usual way you all know from elementary courses, right? In maybe linear algebra or calculus, wherever. So it's just a set of pairs where x is coming from E and y is coming from G. And of course, you can talk about the Cartesian product of any two sets, right? So similarly, for D being a subset of E and F being a subset of G, we can talk about D cross F. Okay, thank you. So by a measurable rectangle, we mean a Cartesian product, let's say D cross F, of two measurable sets from different spaces. So D is measurable in the first space, and F is measurable in the second space. So let me draw a measurable rectangle on the two-dimensional Euclidean space. Let's say you have this interval, 2 to 5. So this is our E, and this is our G. One, 3, and 4. Okay? So this point is not included, and these 2 points are not included. So the Cartesian product of those two sets, so this is my F, and this is my D, right? So D cross F is what? Well, so let's be careful. Let me draw a rectangle here, okay? And let's decide which parts of the boundary are included. First of all, this part is not included, right? Because this point is not included. So this part is not included. How about this part? This part, is this included? No, right? Because 2 is not included. Similarly, this part is not included, but this part is included. This part, without its corner points, is included. And also the interior. Of course, the interior is included. Okay. Now what? Now we have 4. We're going to include the line segment except for its endpoints. So this is the union of those two pieces is the Cartesian product of D and F. Okay. So this is something that we call a rectangle, measurable rectangle. Measurable because the two parts, D and F, are measurable subsets of R. Borel measurable in this case, in this example. Okay. So we're going to look at the collection of all such measurable rectangles. And can you guess what we're going to do with them? You have a collection of measurable rectangles, some sets. What can you do with that collection? You can intersect them and get another rectangle, right? So that is a pi system on E cross G. And what can you do with that pi system? Yes?
You can use momentum class to show.
To show what? First, we need a sigma algebra, right? Before doing that. So let's generate something out of them. Let's generate the sigma algebra. Let's look at the sigma algebra generated by the collection of all those measurable rectangles. And that is what we're going to call the product sigma algebra. Okay? This is the way to define a sigma algebra on the Cartesian product. So the sigma algebra E product G, written this way, okay, defined as the sigma algebra generated by the collection of all measurable rectangles is called the product sigma algebra on E cross G. So in other words, script E cross script G is nothing but the sigma algebra generated by measurable rectangles, D cross F. D is in E, F is in G. And as we have just noticed, this is a pi system on E cross G. Just observe that this is a pi system. Well, you can just see it on picture, right? If you have two rectangles, their intersection is another rectangle, is also a rectangle. Of course, this is not a proof, but at least gives you some intuition. So what does this product sigma algebra contain? Well, it contains all possible sets that you can generate by using countably many measurable rectangles, right? You can look at their countable unions, countable intersections, set differences, etc., etc. So a set in the product sigma algebra is not necessarily a measurable rectangle anymore, but it can be, for instance, the complement of a rectangle, or it can be the union of two rectangles, which is not a rectangle, right? The union of two rectangles is not a rectangle anymore. And if you have countably many rectangles, you can even create shapes that are not really polyhedral. Okay? So in fact, on R2, the product sigma algebra, namely the product of the Borel sigma algebra here and the Borel sigma algebra here, contains pretty much all the sets that you can imagine. Okay? So it doesn't have to be a nice geometric shape. It can be very ugly, and it is still Borel measurable, just like in the one-dimensional case, right? The Borel sigma algebra on the real line has all the ugly sets that you can imagine, and the same is true in the higher dimensional spaces. Okay? So let me write as a remark that so E cross G contains all measurable rectangles their countable unions, intersections, complements, and further sets generated by further sets further countable unions, etc., of these unions, intersections, etc., unions, etc. So it is quite rich. It is quite rich. And as an example, you can look at the Borel sigma algebra on the real line. So let's take E and G are the same, and E and script G are also the same, okay? So now we have R2 with the Borel sigma algebra product, Borel sigma algebra on R. So this is what we call the Borel sigma algebra on R3. We simply call it Borel R3, the Borel sigma algebra on R2. So maybe one warning is that this product sigma algebra is not the set of all Cartesian products of two measurable sets. Okay? So it is not, otherwise it would be just equal to the collection of measurable rectangles. Okay? So it contains sets that are measurable rectangles, but also many more sets. Okay? So it is not just a collection of measurable rectangles, but the sigma algebra generated by the collection of those measurable rectangles. Okay? So the collection of measurable rectangles is just a pi system on the product space, the Cartesian product. But you can look at some other sets which are not rectangles, like the union of those two rectangles. Okay? So just a little maybe exercise, a side note, is that you can generate this product sigma algebra in a different way. So E cross script G is also generated by one-dimensional measurable rectangles. Here's what I mean by it, measurable rectangles. So E cross G is generated by sets of the following form. So by a one-dimensional measurable rectangle, I mean to take the first space, the first set as the full space, E, or take the second set as the full space, which is G. So you either look at E cross F, where F is coming from script G, or you look at D cross G, where D is coming from the first space. Okay. So in this picture, a one-dimensional rectangle is something like 2 to 5, the interval 2 to 5, cross R, which is like this whole region, right? Or the other way around, you look at this set, R cross this set, which is this whole thing, right? Going to minus infinity and plus infinity like that, okay? So these are the one-dimensional rectangles. Here you take E, the first set, as the full space, and here you take the second one as the full space. That's why we call them one-dimensional. Of course, they live in the product space. They are subsets of the product space. Is this clear? Well, its proof is not clear, probably, but just a statement maybe is clear, right? So you can prove it yourself. It's just a side note, okay? Just as an alternative way of defining the product sigma algebra. Well, let me give you one more example, maybe even simpler than this real line. Just finite sets, okay? So what would you expect if you have two finite sets with their power sets, with their discrete sigma algebras. What is the product sigma algebra? Another finite set, right? The Cartesian product is another finite set. So what would you expect the product sigma algebra to be? So you have the discrete sigma algebra on the first space, the discrete sigma algebra on the second space. What is the product sigma algebra of the two discrete sigma algebras that you define this way? Well, which sigma algebra would you like to have on the product space, since it is again a finite set? Again, the power set, right? So since the product of two finite sets is again a finite set, you would like to have the sigma algebra being equal to the power set, the discrete sigma algebra. And indeed, it is the case. Indeed, it is the case. So let me write, let's say E and G are finite sets with discrete sigma algebras, with their discrete sigma algebras. Then, so namely, E is 2 to E and script G is 2 to G. So one can check that the product of script E and script G is nothing but the power set of E cross G. And I think this is even true for countable sets. Let me write countable sets. And for sure, we know that E cross G is a countable set. Right? If you have points like 1, 2, 3, and points like 1, 2, 3 here, then you can count them, right? This is your product space. So you can count it as 1, 2, 3, 4, 5, 6, etc., etc. The new 1, 2, 3. This is a recall from the very first lecture, I guess. Right? Okay. Any questions so far? Exactly. So you can have, so this line segment, forget this part, this is also a rectangle. So rectangle in a general sense. Okay. So, well, we said this collection is a pi system, okay? But maybe we would like to have a simpler pi system, okay? Let's say you have a pi system that generates this sigma algebra and another pi system that generates this sigma algebra, okay? Can you look at the collection of measurable rectangles which are formed as Cartesian products of sets coming from the pi systems of the individual spaces? Let's say you have a pi system here, you have a pi system here, and you just look at measurable rectangles formed as products of sets coming from the pi systems, not from the full sigma algebras. What do you obtain? Hopefully this is a simpler, a smaller pi system that generates the product sigma algebra. Okay? So let's look at this case. That's a proposition. Okay? So, and our motivation is that can we have a smaller pi system on E cross G, generating script E cross script G. Okay, okay. So let P1 be a pi system on E such that it generates script E, and let P2 be a pi system on G such that it generates the script sigma algebra, the sigma algebra script G. Okay. And let us define P, which is the collection of measurable rectangles of a special form. So D has to come from P1, or it is equal to the full set. So you allow for a one-dimensional rectangle. And F is coming from P2, or it is equal to the full set G. Then P is a pi system on E cross G such that it generates the product sigma algebra. Maybe before the proof, we should give an example just to clarify what we mean, okay? Let's look at an example. Okay? So let's take E as the real line and take also G equal to the real line, and take P1, P2 as the collection of intervals. Of this form. This is the pi system that we used a lot because it has connection with, it is the basis of cumulative distribution functions, right? So just look at this pi system on the real line and do the same for both spaces. So the two spaces are just identical, and you look at the same pi systems. So what is this collection P here? Well, if you look at this pi system union the full set is, well, not included here, so we need to include it, okay? So let's look at minus infinity to B1 cross minus infinity to B2, okay? So B1, B2 are in the real line. And let me write it this way. Well, R cross B2, B1 cross R, or R cross R. Okay? So you allow for those other possibilities, which you can see as kind of corner cases, right? You let B go to infinity, and this is what you get. Well, if you would like to write it in full, here's what we have to do. And this is a singleton. So we have that. So the proposition gives that this is equal to sigma of P. And you can further show that, we can further show that the first part is just enough. first part is just enough, because you can generate R cross an interval as a countable union of just rectangles of this form, right? It is just, you can just take maybe minus infinity to n and let n go to plus infinity as a countable union, right? That's going to give you R cross a rectangle. Let me write. So R cross minus infinity to B2 is the countable union of B, let me say n from 1 to infinity. So in fact, you can, using this theorem and some further simplifications, you can show that the Borel sigma algebra on R2 is generated by all sorts of rectangles, okay? Just like in the one-dimensional case. You don't have to look at intervals of this form, but you can look at intervals of any form. A to B, A to infinity, A included, A excluded, etc., etc. You can take products of any sorts of intervals. And they don't have to be, you don't have to take the same structure for both spaces. You can look at intervals A to B here and intervals minus infinity to B2 on the second space. They don't have to be the same pi system, right? They're just free. Is the example clear? Yes?
Can you go over that P again?
Sure. So this P is defined as given here, okay? So ideally, we would just like to look at rectangles, which are real rectangles like this, okay? But since we have to include also the full space case, we have all sorts of possibilities. So a set from P1 and a set from P2, that's the first case. A set from the full set from the first space, and a set from the second space, second pi system. It is the second type. A set from P1 and the full set on the second space. It gives you the third case. And you take R and R, you get the fourth case. Okay? But you don't really need the second, third, and fourth cases. This first one is just enough. But that is not coming from the proposition. You have to check it separately. It's a further result. Okay. So let's prove our result now. Okay? Let's prove our result. So we would like to prove that sigma p is equal to E cross G, script E cross script G. Okay, so we need to prove an equality, so we have to look at two cases, right? Two parts. So sigma p is a subset of E cross G. Let's prove this. Well, I have to write proof somewhere. Proof of proposition. So sigma p is a subset of E cross G. Well, what is P first of all? Is P a subset of E cross G? Is P a subset of E cross G? Well, of course, because P is just some measurable rectangles of a special form. For free, these are measurable rectangles. Look at the measurable rectangle definition here, right? For sure, the sets in P are already measurable rectangles, right? So every set in P is, by definition, a measurable rectangle. So P is a subset of E cross G. Since the second is a sigma algebra, we have some preliminary lemma, right, in the very first chapter, very first section, right? If you have any collection which is a subset of a sigma algebra, then the sigma algebra must also contain the sigma algebra generated by this little collection, right? So, let me say, since E cross G is a sigma algebra, we have sigma P is a subset of E cross G. So this shows the first part. Okay. And for the second one, we're going to do a similar trick for the second part. So E cross G is a subset of sigma P. How can we show that? Well, if we can show that the collection generating this sigma algebra, which is the collection of measurable rectangles, are in this sigma P, then the sigma algebra generated by those measurable rectangles, which is this sigma algebra, is also in sigma P. So it is enough to show that every measurable rectangle is in sigma P. Because if every measurable rectangle is in sigma P, then the sigma algebra generated by those measurable rectangles must also be a subsigma algebra of sigma P. Okay? Just the same type of lemma that we use. It is not monotone class argument or anything. Okay? Okay. So what do we know? What do we know? We know D cross F is in sigma P for every D in P1 and F in P2. Because these are sets in P, so we know it. Of course, we know it, right? These are just, this D cross F is just in P, therefore it is also in sigma P. We would like to show further that D cross F is in sigma P for every D in E and F in G. So not only the sets coming from the pi systems, but also for the sets coming from the full sigma algebras generated by those pi systems. So this generates this sigma algebra, and this generates this sigma algebra. This is what we know. This is what we would like to show. Well, I guess we need to give a break before we continue.